Hello everyone, welcome back to my YouTube channel. In this particular video, we'll be looking into a very interesting algorithm for finding out the communities in a given network. The algorithm is known as Girvan Newman algorithm. So first, let's have an overview of this algorithm. So basically this algorithm is used to detect the communities in a given complex network. Now, what is this community? Let's see that first. So this is the definition of communities. Communities can be thought of a group or collection of nodes that have similar roles or functions inside a given network. That means those groups of nodes which work for a particular task or their functioning is similar to each other, that group of nodes is called as community. They share the same characteristics or attributes. To identify a community is an important task, and for identifying those communities, we require this Girvan Newman algorithm. This is not just one algorithm to find out the communities, but yes, this algorithm is widely used to do that. Let's have an example of communities. Let's say in an online discussion forum, for example, Quora. There, the users who share common interests or they engage in frequent discussions might be called as a community. Now, in a similar fashion, let's see another example. So, the next example is that in a co-authorship network, a community might be a group of researchers who frequently collaborate on research projects in a particular field. That means the users are constantly working on a particular field or they are researching on a particular topic. This can be called as a community. So I hope till now you might have got an idea of what communities are. So this Girvan Newman algorithm is basically used to detect those communities in complex networks. This algorithm is effective for hierarchical community structure. We'll see this point in details later on. Now, this Girvan Newman algorithm is based on the strategy of betweenness centrality, which we have already discussed in the previous video. If you haven't watched the video of betweenness centrality, then you can surely watch it in the Big Data Analytics playlist. So this algorithm is purely based on betweenness centrality concept. It identifies the natural boundaries between communities. That means it is going to separate communities from each other. It is going to group the like-minded nodes and will separate the nodes which works or functions differently from the previous one. You can think of this Girvan Newman algorithm as a clustering algorithm. Basically, it is going to cluster in the network. It is going to form the clusters of like-minded nodes. That means those nodes which functions similar to each other. Now, to be precise, it uses the divisive hierarchical clustering concept. Basically, at first the entire network will be one cluster and then it is going to divide the network into group of clusters based on the algorithm strategy. Also, it provides a hierarchical view using the dendrograms concept. We'll see it later on. Now, this Girvan Newman algorithm is widely used in analysis of social network. Yes, that social network where you waste most of your time daily. Now there is a drawback of this algorithm, and the drawback is that it is computationally intensive. That means for finding out the communities, it is going to iterate over every single node and will find out all the possibilities regarding it, which makes it a lengthy and tedious process, and therefore it may not be feasible for very large networks. It requires high computational resources. So now I hope that you might have got an overview of this Girvan Newman algorithm, and if so, then we'll move on to the algorithm. So the Girvan Newman algorithm is based on simple 4 steps. First step is to calculate the betweenness centrality of all the edges in the network. Now for calculating the final betweenness centrality of all the edges in a network, we'll have to consider every single node as the root node and then find the betweenness centrality of all the edges with respect to that root node. Don't worry, I'll show you one example and I'll tell you the step-by-step solution for calculating the betweenness centrality of all the edges. Now once we calculate the betweenness centrality of all the edges, now the next step is to remove all the edges with the highest betweenness centrality. Betweenness centrality is just a number. Whichever edge has the highest betweenness centrality, we'll just remove that. Now, once we remove the edge with the highest betweenness centrality, whichever nodes with edges are remaining will have to again calculate the betweenness centrality of the remaining portion. And for doing that, again we'll have to follow the same procedure. Again, after calculating the betweenness centrality of the remaining portion, we'll again have to remove the edge with the highest betweenness centrality from the remaining portion. That means we are repeating the step 2 and 3 continuously, and we need to repeat these steps until we get the desired number of communities in the given network. So this was the algorithm. The algorithm is very simple. I hope it is clear to you all. Now, with the help of this algorithm, we'll solve one example. This example will surely clear all your doubts for finding out communities using Girvan Newman algorithm. So, we'll have to find out the communities using the GN algorithm for the following graph. And you can see that the graph contains 6 nodes. The nodes are connected to each other in this fashion. You can also see that the edges here in this graph are bidirectional. That means node A can move to B as well as node B can move to node A. So I hope the question is clear to you all. Now we'll have to compute the betweenness centrality of all the edges with respect to every single node, starting with node A. So consider node A as the root node. So now we'll have to construct a tree-like structure keeping root node as A. So let's start with the process. So you can see that we are considering root node as A. So here we have considered the A node first. Now you can see from A node we can reach directly to C and B node. That means the child of A node is B node as well as C node. So the graph will look something like this now. Basically we are following the BFS algorithm, that is the breadth first search algorithm. Now moving to node B, you can see that node B can directly reach to node D as well as to node F. So the child of node B will be F and D. After node B, we encountered with node C. You can see that node C has direct reach to node D as well as node E. Hence, you can draw the graph something like this. You can see that node D is the child of node B as well as node C. So the entire graph will look something like this. Now we will have to calculate the weight of each node. Weight of the node is nothing but the number of shortest paths that are present for reaching from the root node to that particular node. Now you can see that for reaching from the root node A to A itself, we have only one single path, therefore weight of the root node will be 1. Similarly, for reaching from the root node A to B and C, we have only one single path, that is AB and AC respectively. So hence the weight of node B and C is 1. Similarly, for reaching from root node A to F, we have only one single path. So weight of node F will be 1. Now for reaching from node A to D, we have two shortest paths, that is ABD as well as ACD. So the weight of the node D will be 2. Now for reaching from A to E, we have only one single shortest path, hence we'll write 1 as the weight of the node E. Now once we calculate the weight of each node, now we'll have to calculate betweenness centrality of each edge with respect to the root node, starting from the leaf nodes. So we'll start from the leaf node F. So you can see that whenever the scenario is when you are finding the edge weight which is attached to the leaf node, then it is straight away given as the next node weight divided by the leaf node weight. So here you can see that the edge betweenness will be 1, which is the node weight of B, divided by the node weight of F, which is 1. 1 divided by 1 is 1. Similarly, for the edge BD, the weight or the edge betweenness of the edge BD will be 1, which is the node weight of B, divided by 2, which is the node weight of D, which is 0.5. Similarly, for the edge CD, it will be 1 by 2 again, which is 0.5. For the edge CE, we have 1 as the node weight of C as well as 1 as the node weight of E. 1 divided by 1 will be 1. So we have calculated the edge betweenness of all the edges which are sticked to the leaf node. Now we'll try to calculate the edge weight or the betweenness centrality of the edge AB. So this is an edge which is not directly stick to the leaf node, it is stick to the non-leaf node. So in this particular case, you will also have to consider all the edges that node B had. Like here, node B had the edge BF and BD. So we'll have to consider these two edges also when it comes to a non-leaf node. So we'll add the edge betweenness of these two edges, that is 1 plus 0.5, plus we'll also have to add the node weight of A divided by the node weight of B, which is 1, divided by 1, which is 1. So in all, 1 plus 1 plus 0.5 comes out to be 2.5. So 2.5 is the edge weight of AB. Similarly, for AC, you can see that two edges CD and CE are incoming to it. So we'll also have to consider it while adding. A has a node weight of 1 and C also has a node weight of 1. So 1 divided by 1 will be 1. As well as with that 1, we'll also have to consider the 0.5 from the edge CD and 1 from the edge CE, which sums up to 2.5. So I hope it is clear how to calculate the edge betweenness for with respect to every root node. Now we'll have to consider the next node, which is B node, as the root node. Now again we'll have to construct the graph, but this time we'll have to consider the root node as B node. So let's start constructing the graph. So we will have the root node as B. Now you can see that in the graph, B node is directly reaching to node A, D and F. So here B node will have the child A, D and the third child will be F. Now similarly, we'll move on to the next node, that is A node. So again you can see that in the graph, A node is directly reaching to the node C. Only C is the child of A node. So hence we'll write C from A. Next is D node. D node is directly reaching to the node C. So we'll join it with the C node. And again you can see that the next node is F. F node does not reach to any other node directly. Hence we'll move on to the C node. Now you can see that C node is directly reaching to the node E. So this is the final tree that we have constructed considering the root node as B. Now we'll have to find out the node weight of every node. First is the B node. You can see that there is only one way to reach from B to B. So therefore 1 will be the node weight of B. Next is the node A. You can see that there is only one single shortest path that is present for reaching from the root node to the A node. Hence the node weight of A is 1. Similarly for D and F, the node weight will be 1. Now you can see that for reaching from B, that is the root node, to the C node, we have two paths, that is BAC and the second path is BDC. Hence the node weight of the C node will be 2. Next node is E node. You can see that for reaching from the root node B to E, we have two paths. One is BACE and second is BDCE. So hence the node weight of E is 2. Now we'll have to calculate the edge betweenness of every single edge starting from the leaf nodes. So as I said, the rule is very simple. For calculating the edge betweenness of the edge which is stick to the leaf node is simple. It is just the division of the node weight of the next node divided by the node weight of the current node. So 2 divided by 2 will be 1. Now you can see that for the next edge, which is AC, we'll also have to consider the edge CE. So the edge CE has a weight of 1. So 1 plus. Now C is a non-leaf node. Now always remember one short trick, that the weightage of every single non-leaf node will be 1 only. When you are calculating the edge betweenness, you will have to consider the weightage of every single node as 1. So now the weightage of the node C here, considering it as a non-leaf node, it will be 1 plus the previous edge betweenness, that is CE, is 1. So 1 plus 1 is 2. And now since C is split into two parts, therefore we'll have to divide the edge betweenness of the edge AC. That is 2 divided by 2 is 1. So the edge betweenness of AC is 1. Similarly, for calculating the edge betweenness of the edge CD, we again have the CE as the previous edge. Considering that, we'll add it with the weightage of the node C, that is 1. 1 plus 1 will be 2. Therefore, 2 will be divided by 2 since it is splitted into 2, which will be 1. So the weightage of the edge CD will be 1. Now for the edge AB, you can see that the previous edge is having the weightage 1, which is the edge AC. So 1 plus the weightage of the node A is 1, 1 plus 1 is 2, so edge weight of AB is 2. Similarly for the edge weight of BD, the value is 2 because the previous edge weight is 1 and node weightage of the node D is 1. 1 plus 1 will be 2. Now for the edge BF, the weightage will be 1 because it is a leaf node, so 1 divided by 1 will be 1. So I hope it is clear. So now we'll calculate the edge betweenness of every single edge for node C, considering the root node as C now. So you can see that C has 3 child. It can reach directly to the nodes A, D and E. Now considering the A node, you can see that A can directly reach to the node B. So B will be the child of A. Next node is D. D can directly reach to only one single node, that is B. So D has a child B. Next, E node has no direct connection with further nodes, hence E won't be having any child. Next, B node is having direct connection to the F node, hence we'll draw the child of B as F. Now we'll calculate the node weightages. So here the node weight of the root node will be 1. Now there is only one single path for reaching from the root node to the node A, D and E. So the node weightages of A, D and E will be 1. Now there are two paths for reaching from the root node C to B. The first path is CAB and the second path is CDB. So the node weightage of the node B is 2. Similarly, for reaching from the root node C to F, we have two paths. First is CABF and second is CDBF. So node weightage of the F node is 2. Now we'll calculate the edge betweenness. So since F node is the leaf node and the edge BF is directly connected to the leaf node, the simple formula is the next node weightage divided by the previous node weightage. So 2 divided by 2 is 1. Now AB is an edge which is connected to a non-leaf node. So as I said that by default each node will have a weightage of 1. Here node B will by default have a weightage of 1. So 1 plus the previous edge weight, that is 1, will be 2. So 1 plus 1 is 2, and since node B is splitted into 2, BA and BD, so therefore the weightage 2 will be divided by 2. Hence the edge weight of the edge AB is 1. There is a similar case for the edge BD, and therefore the edge BD will have a weightage of 1, same as the weightage of AB. Next edge is AC. So you can see that the AC edge has the previous edge as AB, whose weight was 1. So 1 plus the current node, that is A node's weightage is 1. So 1 plus 1 is 2. Hence the weightage of the edge AC is 2. Now the next edge is CD. You can see that CD has a previous edge as 1. So 1 plus the weightage of the node D, 1, which will be equal to 2. So CD has a weightage of 2. Next is CE. You can see that it is a leaf node. So 1 divided by 1 is 1. So I hope it is clear. Now similarly we'll calculate for the node D. Considering this time node D as the root node, we'll draw the tree. So you can see that D is the root node. You can see that in the graph D can directly reach to node B and C. So it will be having two child B and C. Now the next node is B. B can directly reach to A as well as F. Hence B will have two child F and A. Now the next node is C. C can directly reach to A and the node E. Hence C will have two child, one is A and the next will be E. So join CA and CE. This is the graph. Now in this particular graph we'll have to now calculate the node weights of every single node. Starting with the root node, you can say that the root node has a weightage of 1. Next is the B node. You can see that there is only one single path for reaching from the root node D to B. So the node weightage of B is 1. Similar case for C, the node weightage of C will be 1. Now there is only one single path for reaching from D to F. Hence F has a weightage of 1. Next, you can have two paths to reach from D to A. One is DBA and second is DCA. So 2 will be the weightage for A and 1 will be the weightage of E. Now we'll have to calculate the edge weight. For every single edge that is connected to the leaf node, it is very simple. You just have to divide the next node weightage divided by the current node weightage. 1 divided by 1 is 1. So BF will have a weightage of 1. Similarly, BA will have a weightage of 1 divided by 2, that is 0.5. Now CA will have a weightage of 1 divided by 2, which is 0.5, and CE will have a weightage of 1 divided by 1, which is 1. Now the next edge is DB. You can see that the edge DB has two previous edges. One is BF and second is BA. Considering these two, we'll have to add the edge weights of these two, 1 plus 0.5 plus the node weightage of the node B, which is 1. Now again I am clearing one thing. For every non-leaf node, don't look at the node weights. By default, the node weights is always 1. Even if let's say there is any other number written, then also consider the node weightage of any non-leaf node as 1 only. So 1 plus 0.5 is 2.5. Now similarly for the next edge, CD will have two previous edges, that is CA and CE. The weights of those two edges are 0.5 and 1 respectively. Add them and add the weightage of the node C, which is 1 again. So 1 plus 0.5 is 2.5. So I hope this graph is clear. Now you can pause the video and try to construct by yourself the next two remaining graphs. Okay, now this time we have the root node as E. You can see that E has one single direct child, that is C. Next, C node has two child or two direct connection to node A and D. So C will have two child, A and D. You can see that A can now directly reach to B and D also can directly reach to B. So A and D will have child B. B can now directly reach to F. So B will have a child F. Now we'll have to calculate the node weightage of every single node. You can see that E and C will have the weightage 1. Similarly, A and D will also have a weightage 1 since it is directly reachable from E to that particular node with one single path. Now you can see that for the node B, you have two paths. One is ECAB and second is ECDB. Similarly, for the node F, you have two paths, hence the node weightages of both these nodes will be 2. Now we'll have to calculate the edge weight starting from the leaf node. So since this particular edge BF is directly connected to the leaf node F, so the formula is 2 divided by 2, which is nothing but the next node weight divided by the current node weight. So the weight of BF edge is 1. Next edge is AB. You can see that there is one previous edge to the edge AB, which is BF. Considering that weight also, you will now have to add the weight of the node B. B is a non-leaf node, hence by default its weight will be 1. So 1 plus 1 will be 2. Now since the node B is splitted into two parts, that is BA and BD, hence we'll divide this 2, that is we'll divide the edge weight of AB by 2, that is 2 divided by 2 will be 1. Similar case for the edge BD, we have one previous edge as BF which has a weight of 1. 1 plus the weight of the node B is 1. 1 plus 1 is 2 and you have to divide it by 2 because B is splitted into two parts. Now the next edge is AC. You can see that there is only one single previous edge to the edge AC, that is AB. So considering the weight of that edge AB also, so 1 plus the node weightage of the node A is 1. So 1 plus 1 is 2. Hence the edge weight of the edge AC is 2. The similar case is for the edge CD. The edge weight of CD will be 2. Now the next edge is EC. You can see that there is two previous edges to the edge EC, that is CA and CD. Hence add both the weightages of them, that is 2 plus 2, and also add the node weightage of C, that is 1. So 2 plus 2 plus 1 is 5. So I hope it is clear. Now it's the last node to calculate the edge betweenness of all the edges. So considering the F node now as the root node, we'll have to construct the tree. So F is directly reachable to B, B is directly reachable to A and D, A is directly reachable to C, D is also directly reachable to C. Now C is directly reachable to E. Now we'll calculate the node weightages. As you know that root node always has a weightage of 1. Now B node is directly reachable from F with one single shortest path, hence the node weight of B, A and D will be 1. Because there is only one single path. Now you can see that for reaching from F to C we have two paths, that is FBAC and FBDC. So hence node weight of C node will be 2. Similarly for reaching from F to E we have two paths, FBACE and FBDCE. So hence the node weightage of E node will be 2. Now we'll have to calculate the edge betweenness of every single edge starting from the leaf node edge. So the edge is connected to the leaf node, therefore the formula will be the next node weightage divided by the previous node weightage, which is 2 by 2, which is 1. Next edge is AC. AC edge is having the previous edge as the CE edge. So considering the weightage of the edge CE, that is 1, plus the node weightage of the node C is by default 1 since it is a non-leaf node. 1 plus 1 is 2. Now since C node is splitted into two parts, that is CA and CD, hence we'll divide the weightage 2 divided by 2, that is 1. Similar case for the edge weight of DC, it will be divided by 2, so it will be 1. Next is AB. AB has one previous edge as AC, so 1 plus the non-leaf node A weightage 1, which is 2. Next is BD. Again BD edge will be having the weightage of 1 plus 1 will be 2 because it has a previous edge DC also. Next is FB edge. FB edge has two previous edges, that is BA and BD. Add the weight of both of them, that is 2 plus 2, and the node weight of the current node B, that is a non-leaf node, which is 1 by default. Hence 2 plus 1 plus 2 will be 5. So I hope it is clear. Now that we have calculated the edge betweenness of all the edges considering every single node as the root node, now we'll have to construct this table. So this table has 3 columns. One is the all the possible edges, the next is the betweenness centralities of all the edges with respect to every single node, and final column is the total column. So you can see from the graph we can have one edge as AB. The next edge from the graph can be considered as AC. So we'll write it inside the table. The next edge from the graph is BD. So we'll write it inside the table. Similarly, we'll be having the next edge as BF, and the next edge will be CD. And lastly, we'll have one possible edge as CE. So we have written all the edges. Now let's start filling this table with the values that we have computed so far by constructing the graphs. So now we'll have to consider all the graphs that we have previously constructed by considering every single node as the root node. You can see that for the edge AB with respect to the column A, that means the root node is A here. You can see that the weightage of the edge AB in that particular graph is 2.5, hence we have written 2.5. Similarly, for the node B as the root node, the edge weight for AB is 2. Now the next graph is of the root node C. In that graph, the edge weight of AB is 1. Now in the next graph with respect to node D, the edge weight of AB is 0.5. Similarly, in the next graph, which is with respect to the node E as the root node, the edge weight of the edge AB is 1. Similarly, for the F, the edge weight of AB is 2. Now we have filled all the values for AB. We just have to sum up all the values and write it in the total column. So the total of all these values is 9. So hence the edge betweenness centrality of the edge AB is 9. Similarly, we have to do it for AC. So from all the graphs, the weights of the AC will be written under the respective root node column for the edge AC, and after filling that, finally we'll have to sum up all the values. So you can see that the values are 2.5 for node A, 1 for node B, 2 for node C, 0.5 for node D, 2 for node E, and 1 for node F. This is for the edge AC, and the total comes out to be 9. Similarly, we'll have to do it for BD, BF, CD, CE also. So you can see that for BD we have got the edge betweenness centrality as 9. For BF we have got the betweenness centrality as 10. For CD we have got the betweenness centrality as 9, and for CE we have got the betweenness centrality as 10. So I hope up till now it is very much clear to you all. Now once we calculate the total values, write all of them in place of all the edges inside the original graph that we have got in the question. So we have filled the edge weights of every single edge in the graph. Now one thing you need to note that since all the edges here are bidirectional, Therefore, the betweenness centrality of every single edge will be reduced by half. We'll have to divide it by 2. So 9 by 2 is 4.5 and 10 by 2 is 5. So we'll now write the new values again for this particular graph. So you can see that now the graph will look something like this. The edge weights are reduced by half. Now once this is done, the next step as per the algorithm is to eliminate the edges with the highest betweenness centrality. You can see that from this graph there are two edges, that is BF and CE, with the highest betweenness centrality as 5 compared to the other edges. So we'll have to remove these two. And after removing these two edges, you can see that the graph is separated into 3 sections. Now you can see that as per the algorithm, the work has to be done on the remaining graph. So you can see we have covered the first 2 steps. Now in the third step, we can see that it is asking us to recalculate the betweenness centrality of all the remaining edges. So in the graph, if you remember, we had 4 nodes connected to each other, and this is the leftover portion of the graph. Now again, for this particular portion, we'll have to compute the same steps, that is to draw the graphs, that is the tree-like structure for every single node as the root node. You can notice one thing, that this graph is symmetric. Each node is connected to other 2 nodes. So just by seeing, we can predict that edge betweenness of all these edges will be one and the same. But just to have a confirmation, let's quickly draw the graphs for every single node as the root node and calculate the edge betweenness as well as the node weight. So for node A, the graph will look something like this. You can see node A is directly reachable to node B and C. Next, B node is directly reachable to D node, and C node is also directly reachable to D node. And finally we compute the node weights. A, B and C will have the node weights as 1, and the node D will have the node weight as 2, because it can have 2 paths to reach from the root node A. That is, one is ABD, second is ACD. Next we calculate the edge betweenness of every single edge starting from the leaf node. For BD it is simply 1 divided by 2, for CD it is 1 divided by 2 again, and for AB it is the previous edge weight plus the non-leaf node weightage, which is 1.5. Similarly for AC. Now similarly we'll compute the edge betweenness by considering every single node as the root node, and these will be the 4 graphs, and after that we'll calculate this particular table, and finally we'll sum up all the values for every single respective edge. Now you can see that in the total section we have got the betweenness centrality of all the edges as 4. I already said by looking at the graph only you can understand whether the betweenness centrality will be same or different. So now let's come back to the graph and write all these values. So 4 is the betweenness centrality of all these edges. Now as I said that since this is a bidirectional graph, we'll divide the betweenness centrality of all the edges by 2. So 2 will be the betweenness centrality of all the edges now. Now as per the algorithm, the next step is to eliminate the edges with the highest centrality measure. So you can see all the edges are having the same centrality measure, so we'll eliminate all of them. But now by looking at this particular figure, don't you think that this is not at all a network now? Because here no node is connected to any other node. So therefore it's better not to remove the edges. By looking at this situation, you should understand that this is the only point where you need to stop calculating the betweenness centrality of the remaining portion. So finally you can say that the node E is one independent community. The second portion, that is the collection of node A, B, C and D, is one independent community, and the node F is another independent community. So these 3 are the final independent community in the given network. Doesn't that look like clusters? Hence, this Girvan Newman algorithm is also called as a clustering technique, which is used to cluster the communities from the given network. So I hope the ideology of entire Girvan Newman algorithm is clear. No doubt some steps in between are little confusing, but by looking at the steps once or twice again will surely clear all your doubt. So now I hope the entire algorithm as well as the example is clear to you all. Now one request to you all, please share this video with your friends, as well as you can also share the entire big data analytics playlist with your friends, so that they will also get benefit out of this. Hit the like button if you like this video. Also hit the subscribe button and don't forget to hit the bell icon. Follow me on Instagram and thanks for watching.